This is a series of notes that covers fluorescence and composition, specifically the use of X-rays to determine the composition both of whole rocks and with some reference to microanalysis as well. This was prepared for mineralogy at Midwestern State University, but should provide a general overview of the use of X-rays to understand the composition of Earth materials. If we want to understand the composition of Earth materials, we're looking for the percentages of elements or elemental compounds that make up that substance. And we need to fingerprint their atoms. One way to do so is to pay attention to the photons that are released when electrons jump from a higher energy position to a lower energy position. When they do that, that jump in energy is discrete and is relatable to the frequency of that photon when it's multiplied by Planck's constant. And of course, we can convert this into wavelengths if we want to by remembering that a frequency is just the velocity over the wavelength. Here depicted as c for speed of light in a vacuum, which is close enough for our purposes. Since electron structure is element specific, we can pay attention to these characteristic wavelengths and frequencies and figure out the concentrations of elements in our material. If you've ever been to a museum that had a mineral display that exhibited fluorescent materials, you were actually experiencing this characteristic radiation in the visible light. When you apply short or long or sometimes both wavelengths of ultraviolet light to some mineral specimens, certain elements within them, called activators, will emit photons in the wavelengths and frequencies appropriate for visible light. And these can be quite distinctive. Fluorescence is that effect. Electrons are jumping, and we're getting the colors we see here. It's probably fair to recall the electromagnetic spectrum at this time, and that visible light occupies a very narrow range of the entire spectrum. Visible light is 700 to 400 nanometers, or thereabouts. We're also going to want to consider the other radiations that can be produced. More importantly, if we work with X-ray radiation, over at the 1 to 0.1 nanometer scale for wavelengths, we would be able to get a much clearer signal of the characteristic radiation. We'll find that you actually have to have elements that are at least as heavy as boron, and that's pushing it, in order to see X-ray characteristic radiation. But it is a very appropriate tool for investigating which elements are present by looking at their characteristic fluorescence. In order to get characteristic X-rays from our sample or analyte, we're going to need a high energy source in order to perturb the electrons. One such source is X-rays itself. These are generated in an evacuated tube where an electron filament applies a high voltage. This directs excited electrons at an anode, which gets very hot and emits a wide range of electromagnetic radiation, including X-rays. Principally, what we're after is the characteristic X-rays that are generated from the anode material itself. The anodes can be made of different things, such as tungsten, rhenium, rhodium, and other elements. The X-rays get generated and they're let out of the tube through a small window, typically made of beryllium film. Beryllium doesn't impede the X-rays, yet manages to hold a vacuum at reasonable thicknesses. So that beryllium window lets the X-rays out into the chamber where they can interact with the sample. X-rays from the tube are going to hit the sample, and that's where these X-rays will excite electrons to make their jumps and allow the elements in the sample to fluoresce their characteristic X-ray radiation. These X-rays produced by the sample atoms are called secondary X-rays, and that's what we're really interested in collecting. We're going to send those through a series of slits, known as a columnator, so that they end up as more or less horizontal, and then direct them towards a crystal with a known lattice structure, set at a particular angle, such that it can diffract our X-rays at specific wavelengths into another columnator, and then hit one of two detectors where we can actually count what's going on. So the key component in this is crystal or crystals of known lattice spacing, such that we can use the Bragg law again, which is n times wavelength, and where n is an order coefficient, n times wavelength is equal to twice the d-spacing times the sine of the angle the crystal is set at. Since we know the d-spacing of the crystal, and we can set the angle to look for specific wavelengths that should occur for certain elements, we can figure out what we're looking at. N is a factor in X-ray analysis, so we have to be wary of higher order Bragg's law satisfaction when we get to the detector. So n equals 1 is usually a common way to think of Bragg's law, but in this instance we might want to pay attention to when n equals 2, and rarely higher than that. There are also other means to excite electrons. One way is to shoot more electrons into the sample. This is typically done in electron instruments, where a wire made out of tungsten can generate at a high voltage excess of electrons that are then directed at the sample through magnets. And this can be a highly focused beam, allowing analysis to happen at small areas, sometimes very much smaller than the width of a human hair. I should mention that there are also particle beams out there as well that send ions to induce ionization, but we probably won't be paying attention to the X-rays generated in the process. Instead, we'll be looking to collect the ions in those instruments. Also, there are laser instruments as well that induce excitation in the atoms when they form ions, as a laser cloud. These tend not to have enough energy to generate collectible X-ray spectra, but instead do produce visible spectra. The key to these is applying a high energy over a small area, which has its applications as well in a process we call microanalysis. Perhaps one of the most common ways microanalysis is conducted these days is inside of an electron instrument. The Hitachi SU3500, shown here, an instrument housed at Midwestern State University, has a detector that is this large gray and blue body hanging off to the left side of the column and stage apparatus. And again, on the right, how this essentially works is a wire gets really excited and sends electrons down a directed magnetic field such that they are focused and hit a small target on top of a sample. When this happens, secondary characteristic X-rays are generated where the beam is hitting that sample volume. The detector hanging off to the left of the instrument is able to collect X-ray signals and make sense of them in terms of how much energy they possess. The process of generating electrons on a small spot has its roots in the development of technology called a cathode ray tube, which was fully exploited as a means for conducting video images in the 20th century. These are the old, heavy TV sets that I certainly remember from my youth. In fact, the picture on the right is not the exact model we have in my house, but very similar. And we thought they were pretty stunning at the time, but, it's pretty easy to see that we have much better visual information these days. How do they work? Again, a high voltage is applied inside a vacuum, in this case encased in a glass tube, a vacuum tube. That made these sets very heavy and awkward to move around as a consequence of it. The electrons are directed by magnets across the front of the glass tube, which is coated with a visible fluorescing material, a phosphor. And as intensity and position fluctuate, it's able to draw a picture within 60 times a second. So a new picture comes up, and it looks like it's in motion. Electrons are charged particles that can be focused and redirected by using magnets. This old-timey example of TV set is very much similar to what we're doing in an electron instrument by basically sending the electrons from a source through a series of magnetic fields to focus on a point. We can even raster it back and forth across the sample by fluctuating the magnetic field. A few terms that we probably should introduce at this point. Voltage is essential for creating these high energies. Voltage is a potential difference. It's potential energy prorated by the charge. And one way to think about it in terms of these instruments is the amount of punch that you have in energy. Higher values means a deeper penetration into the sample and a bigger kick to the atoms. One of the units we use in talking about voltage is the electron volt. This is technically the kinetic energy gained or lost by a single electron accelerating from rest through an electric potential difference of 1 volt in a vacuum. 1 volt at 1 joule per coulomb multiplied by the electron's elementary charge, which is shown here, 1.6 times 10 to the minus 19 coulombs. Another important attribute of this is how the charge is actually moving, and that is current. You could think of it as the quantity of punching. The higher the current, the more these intense punches hit our sample. A higher value means more emission from the sample when it's all said and done. The unit for this can be the microamp or the milliamp, depending on the instrument. Perhaps the most common and simplest electron instrument detector is known as EDS or EDX or sometimes EDAX. And this is an acronym for Energy Dispersive Spectrometry or Energy Dispersive X-ray Spectrometry. Essentially, the process is that we generate an electron spot on the sample that excites electrons, and those electrons then develop characteristic fluorescence, which includes X-rays. Those X-rays are emitted from the sample, and we're able to send a detector down that is able to sense these X-rays and discriminate the energies at which they're arriving. That's the energy dispersive part of it. There are electron instruments that actually use what we call wavelength dispersive spectrometry, which is a little more sophisticated and can be more accurate for analysis, although modern EDS instruments can be highly robust. Wavelength dispersive spectrometry again uses the electron instrument to create the characteristic wavelengths that we're looking for, but here's where we use the Bragg equation in order to figure out what we're looking at. A crystal is set in an evacuated chamber to a series of angles which correspond to the specific characteristic wavelengths that we would be emitting from our sample. And then these are collected in a detector. The detector is able to count the X-rays that are incoming. Both energy dispersive and wavelength dispersive techniques are also used when primary X-rays are sent at a sample They are just two means of detecting X-rays and figuring out composition based on that. But again, wavelength dispersive spectrometry does give you an option to increase the level of accuracy in sample analysis and is used for particularly high resolution and in determining concentration. So regardless of the way we send the energies in to knock the electrons around, the end game from this is generating secondary X-rays that we can then analyze that tell us about the elements that are present in our analyte or sample. When an electron moves from a higher orbital to a lower orbital, and in Bohr and common quantum notation, these would be the n numbers, let's say from n2 to n1, we expect a photon of a specific wavelength and frequency. And again, we will set our system so that we're able to resolve that particular wavelength or frequency or the energy that's associated with it. We'll also note that we don't always use the Bohr notation of n's, but instead use a notation that has letters, K and L, for example. So secondary fluorescence in an X-ray fluorescence machine, where you're using X-rays as a source, sends a primary photon in to our sample or analyte. It then moves electrons around, and we get a secondary photon. In electron probe microanalysis, we are sending an electron in to move the electrons around, and we get a secondary photon from that. The secondary photon is all we're really after, so the means of doing this is all a matter of what kind of scale we want to operate. It would be wrong to think that all the energy we're sending in is going to do the useful work of producing characteristic secondary photons. That's just not the case. And in fact, trying to figure some of this out is a big trick in these analytical instruments. One phenomenon that we will definitely see is that in XRF, or X-ray fluorescence, where we have a primary photon to deal with, we will see scattering of those energies in interacting with the sample. And it's substantial. It's something that you would notice from it. So there's two types of scattering. Either your primary photons go in and they basically bounce off the electrons and come back out with about the same energy they started. That's known as coherent scattering or Rayleigh scattering. Then you also have photons that go in and lose a little bit of energy from their exchanges with the atom, but still come back out. And those are known as Compton scattering or incoherent scattering. Both of these are somewhat characteristic of the material being analyzed and can be used to sort of assess what you're looking at. There are big differences between the scattering patterns of, say, a mineral or silicate-based material and an alloy-based material, for example. In an electron instrument, we actually take advantage of the scattering. The scattering produces electrons that come back at us, and they're at still pretty high energy for bouncing off the atoms. And these have a name in electron analysis known as backscattered. We can actually use this to understand our sample because, as it turns out, things that are made up of heavier elements on the periodic table do a better job of backscattering than things that are light. We can get some initial compositional information from looking at backscattered images by rastering the beam over the sample and looking at the image that's generated from the backscattered electrons. There's more commonly in a lot of electron instruments a process of looking for electrons that have undergone substantial energy loss because one entered the sample and kicked a new one out. So that lost electron is a secondary electron, and these secondary electrons come in at low energy. We can discriminate between these and the backscattered electrons based on their energy, so all we need is a detector that does low energy stuff. That's another tool that when you raster the beam over a sample surface can give you some information about what the sample looks like. What we're after with X-ray analysis is sending an electron in and getting a characteristic photon out. We mentioned this one before. I should say not all those photons make it out in either electron analysis or in X-ray source instruments. Some of the photons then enter another element and kick an electron out, and we'll discuss about this, do other things like move electrons around and get you different photons. But if we consider what happens in an electron instrument where a photon goes in and you get an electron out of the process, those are known as Auger electrons, and they can give you some information as well, but you sort of need a specialized instrument to take advantage of that. When you're shooting a sample with an energetic source, it's important to keep in mind that although in some instances it seems very much like you're just scratching the surface of the sample, there's actually a volume that is interacting with the energetic source. A sampling volume or beam depth. These are actually quite substantial for X-ray sourced instruments like XRF. But they're a serious volume when you consider what's happening in an electron instrument like a scanning electron microscope. I've got a diagram here that sort of speaks to electron instruments, and what happens is the beam hits the surface, and there's actually quite a bit of excitation that happens at depth. Over on the right, I've got the energies and the intensities you can expect to get off the sample, and quite typically, secondary electrons are the most abundant electrons you're going to get. But if we go back to the left again and see that, well, these are only coming from the first 50 nanometers of the sample, and that, for all intents and purposes, is pretty much the surface. So in other words, the secondary electron is a pretty good indicator of what the surface topography looks like on a sample in an electron instrument. And when we think about some of the images you may have seen from scanning electron microscopes, like flies' eyes or flower petals, what you really want to see is the structure that's happening near the surface, and collecting the secondary electrons is the weapon of choice for making great topographical images of surfaces. If you want to know more about how the sample is put together and the relative contrasts in the elemental concentrations, although not directly getting the composition in any robust manner, then you want to go to backscattered electrons. They're much deeperly sourced, they're much higher energy, so they're over on the far right of our diagram to the right. And once again, we see two modes of scattering for these. Elastic scattering, it gives you the biggest signal. And again, this is happening much deeper in the sample. I don't have a number attached to it because this is dependent on what the sample is made of. The same is true for characteristic X-rays. That's a much deeper volume that gets exposed to electrons and generates characteristic X-rays. But again, those are X-rays we can then use to determine composition. Likewise, there is a continuous background that's generated from a slightly bigger volume behind that. Like I said, backscattered electrons and characteristic X-rays and background X-rays are a function of how much energy is being applied to the sample and the composition of the material itself. So for things that are made up of lighter elements, our top left image shows a fairly large sample volume, but if you go to things that are made up of much heavier elements, or a higher Z, then that volume spreads out but shortens with depths. Likewise, if we change the energy of our source, the beam, the voltage that we send in, this is going to give us an increased amount of volume if we go to higher voltage. These are considerations you have to take into account when you're making analyses. Fortunately, there is some help for trying to visualize this. These are known as Monte Carlo simulations. And one particular program that I've used is the Casino program, which tries to predict the pathways of electrons at different energies. So on the left, what we have is a diagram that shows you the penetration depth and scatter of electrons at 7 keV, and on the right, a much different profile. You can see the numbers are even deeper for when you crank it up to 15 keV. So you don't have to go in blind. You can learn a little bit ahead of time on how much of your sample you're going to actually be analyzing. Okay, so again, talking a little bit about electron interactions and the imageries we get out of this. On the left, we have what secondary electrons will get you. And again, these are the electrons that get kicked out from an energetic electron entering atoms. Happens in the first 50 nanometers. Basically gives you the surface topography of a sample. So what you're seeing on the left are a series of yeast cells and what they look like sort of in their full topography. And this would be a good weapon for doing that. You want to be able to characterize what a sample looks like on its surface. You want to go to the secondary electrons. On the right, what you're seeing here is the backscattered electrons that are coming back at high energies. And you're looking at a fairly uninteresting topographical sample. This is a flat, polished rock surface, with the only topography really being a crack that's running through the lower left side. And that's not even interesting topography, it's just a crack in the sample. So what you're seeing here is some variation in the intensity of the backscattered electrons that are coming back at the detector as we raster the beam over the surface. I should specify what we're doing here is taking that energetic electron beam and basically bringing it, much like the old-fashioned TV set, across in straight lines from top to bottom to give us an image of an area of the sample. So on the right, you see bright spots. Those are made up of iron oxides largely. And then darker areas, the darkest grays on this are quartz crystals, and then there are some feldspars that are in the lighter intermediate grays. There also seems to be some other minerals in the field of view that are giving us sort of the higher intermediate light grays. I'd wager those are probably amphiboles. All these instruments sort of have ideal conditions when there's no atmosphere in the way, when we're under a high vacuum. And the reason being is shown on the left for electron instruments. You're not just going to get much signal if you have a full atmosphere's worth of particles in there, nitrogen, oxygen, water, carbon dioxide, etc. It's just going to get in the way of your signal. And that includes the characteristic X-rays as well. Generally, and for really high resolution work, you want to have a high vacuum. That means 1/10 of a pascal or less in terms of pressure. You're at those conditions, you're going to get secondary electrons along with backscattered electrons and characteristic radiation that's unobscured by anything above the surface of your sample. Modern instruments also, electron instruments to be specific, will also operate in low vacuum mode, and the one at MSU does this at conditions from 6 to 600 pascals. So the low vacuum mode will obscure the secondary electron picture, so you won't be able to get secondary electron. You'll get backscattered electrons and characteristic X-ray radiation, although there are some complications with that. One other thing you'll get is you've got this thin layer of atmosphere on your sample, and it fluoresces optically, visibly. And we actually have a detector for that, so we can use that to gain a signal as well. And that's kind of like those crystals in the picture early on in the slide set. It's visibly fluorescing, and we can use the visible information to help us get some knowledge about our sample. At this point, I want to return to the characteristic radiation we're getting through fluorescence, particularly the fluorescence of X-rays from the sample. The example I have mapped out to the right is barium, number 56 on the periodic table. Some things we need to recall about how we're going to talk about this, and what I'm basically going to do is introduce some of the nomenclature associated with X-rays. is that we're going to use Barkla nomenclature. So instead of enumerating the orbital levels as you would in the Bohr system, or talking about quantum mechanics, n equals 1, n equals 2, etc., we're going to use K, L, M, and N. There's also a traditional way to talk about this in terms of Greek letters. This is known as Sieg-Bond notation. It is well instilled in the community. I don't see it disappearing anytime soon. There is a competing IUPAC notation, but I haven't seen that a lot in print, although it makes much more sense than Sieg-Bond notation in terms of how it's notated. Regardless of that, what we're trying to do is characterize some of the radiation we can anticipate from electron jumps that are happening in the atom. So most of the big radiation happens in what we call K radiation. K radiation is jumps from the 2p orbitals and the 3p orbitals. And in these jumps, there are slight changes in the energies that are anticipated depending on the electron configuration from one orbital to the next. So we can discriminate, and although they're very close in energy, between a K alpha 1 jump from the 2p orbital at L3 versus K alpha 2, the 2p orbital at L2. K alpha 1 tends to be the biggest, most intense signal you can ask for from the sample. And then K alpha 2 is somewhat diminished, but very close in proximity in terms of energy. Easily discriminated by energy are K beta peaks, and they tend to be much, much smaller than the K alpha. Then there are L peaks, L alpha and L beta. These are jumps from the 3d orbitals to the 2p orbitals. And then there's even M peaks, but admittedly, M doesn't factor in much into analysis. But that's an F orbital to D orbital jump. The probability of generating an X-ray from primary energy interacting with an atom is known as fluorescent yield, symbolized here by the minuscule omega sign. And generally, fluorescent yield increases with atomic number. There really isn't any fluorescent yield to speak of for hydrogen, helium, and beryllium. So these are not analyzable. And it's not really there for boron, but we'll start it there. It ramps up rather slowly. Then after fluorine, it starts to pick up, and you see higher and higher yields. The fluorescent yield scale is basically a relative intensity scale, so 1 is the max. You can see by the time you get up to elements like barium, you've pretty much hit a plateau in terms of fluorescent yield, and you will not see any increases in fluorescent yield from K radiation. To see L jumps, or L radiation, you really have to be above atomic number 22, titanium, in order to pull that off. L jumps are important for analysis in those heavier elements, but you can see the fluorescent yield doesn't take off quite as intensely as the K radiation does, nor over the natural elements will it reach the fluorescent yield of the K radiation. So the least expensive and least time-consuming way to collect X-rays is through energy dispersive spectrometry. It also sacrifices a little in the accuracy department, so there's a trade-off there. But a modern instrument actually produces a pretty robust analysis using this tool. This is the type of detector that we have on Midwestern State's electron microscope. And they're fairly common in a lot of electron microscope formats these days. And generally, when you buy even a wavelength detection system, you want this along because it's just so much faster to do analyses and can get you a good ballpark value, if nothing else. So let's take a look at what we're getting here. We're getting a report on a graph of energies that are associated with our electrons that are coming in. First rule of thumb is you won't get any more energies than you actually put into the instrument. So if you want to see out to 20 kiloelectron volts, your source, your beam that's exciting your sample, needs to be set at 20 kiloelectron volts. All right, you can see that there are tall peaks here, one for silicon, calcium, iron. These are the dominant concentrations because peak area is actually related to the concentration under which we're exposing the beam, presumably a small dot on the sample. So this small dot is telling us that the analytical volume is dominated by silicon, calcium, and iron, for example. These are K-alpha peaks: silicon, calcium, iron, potassium, titanium, and manganese. There's also, for the getting heavier elements, the L peaks start to show up, and they tend to be lower, but of relative intensity compared to the K peaks over here. And I should specify this one on the left is a K alpha peak. It's K alpha 1 and K alpha 2 together. This is the K beta peak over here. K beta 1 and 3 together underneath this peak. It's not labeled. Generally, the instrument is only really looking at the strongest peaks. So K alpha and L alpha show up and get labeled. The others are along for the ride. The instrument is doing some calculations to turn this into a compositional analysis shown up here. So that can be useful. We can get some data to roll with at that point. Another neat trick we can do with an electron instrument is we can take the beam and run it across the sample, just as we would for mapping out the electrons like secondary electrons or backscattered electrons, except this time we'll pay attention to the X-rays that are being generated and use an intensity scale to show where they are higher and lower for a particular element's radiation peak. So here's the silicon K alpha 1 peak. Basically, we ran the beam across the sample here. There's a whole bunch of silicon right here, lesser amounts here, lesser even amounts down here, and then almost nothing down in this area down here. Well, what is down there? Something that has a whole lot of iron. It's actually an iron titanium oxide. So on the iron K alpha 1 map, we have buku amount of iron down here, and not so much on the other parts of the rastered image. Turning to wavelength dispersive spectrometry, which tends to produce more accurate values for compositions provided care is taken in the analytical procedure. The heart of WDS, or wavelength dispersive spectrometry, is a diffracting crystal that takes advantage of the Bragg equation. This is a crystal of known d spacing, and over on the right I have some characteristics that you definitely want these crystals to have. So they have to have low absorptivity, they got to be able to resolve things, they got to have a reduced fluorescence profile, they've got to not change shape when they get hot, which will happen. They got to be stable under increased X-ray exposure. They got to be machinable or engineered so that they'll fit in the instrument. And affordability is like the last concern, but they can't be so pricey it makes the instrument super expensive. So some common crystals are shown here on the left, and way too much information about them. I would say that the XRF that is used at Midwestern State University, which is a Rigaku Super Mini 200, includes two that are on the list here, an LIF 220 and a PET 002. These are used for different elements to hone in on their characteristic radiation. There is also a third crystal that's a proprietary crystal developed by the instrument maker. I don't have it on here, and I don't know much about its composition. It's kept top secret. When you're generating a peak and wavelength dispersive spectrometry, you want to do it in terms of the rotation of the diffracting crystal, the known crystal, those crystals that were just on the previous slide. This is going to generate a Gaussian peak. These are becoming familiar to us. So you have background, and then you have the peak, and then you come back to background. The amount of particular atoms of an element that are in your sample that is being targeted is directly proportional to the area underneath this Gaussian curve. And fortunately for us, we don't have to measure the area underneath the curve. We can just get some simple curve geometry, peak geometry, and we're done. We can do that by measuring the height of the peak, so knowing the full intensity that we get, say in counts per second, and then measuring background, understanding where background is relative to the peak, because we don't just want the peak intensity. What we want is the peak's intensity over the background. So we can measure 1 or 2 points, and you particularly have to do 2 if your background has some slope, as in some places it does. But at least 1 point and 2 points that give you a position underneath the peak where you can expect the background. And then you want this measurement of peak over background. That too relates to the concentration. We can start to understand our sample through that. There are problems that can arise in wavelength dispersive spectrometry. One of them is that you're looking for the characteristic peak for one particular element. Let's say silicon, for instance. And you might find that there is another element present in your sample that is producing radiation that overlaps with it in 2 theta space. This is something you just have to deal with in one fashion or another. So if we're looking for silicon, that's our analyte in the sample, and we got some other peak that has shown up that's super close to it in some way, shape, or form. There are basically 2 scenarios. Either it's close but distinct, it produces a bigger peak in the dotted line here with a bit of a shoulder on it that's obvious. We might be able to tweak the instrument through careful collimation to get better discrimination. Some instruments don't permit you to do this, so you have to use some techniques where you may want to use this peak but realize that there's another element. Maybe you can analyze that other element from another peak and then back that out of the peak calculation. When you have severe overlap, so it looks like it's just one peak when it's all said and done, you could switch the collimator again to a coarser collimation and decrease the resolution so you get a better sense of what that interfering peak looks like. Again, not an option on some instruments, so you may have to look entirely at other peaks to explain what's happening. So if you have the option for some elements, as you do, to analyze either a K peak or an L peak, and the K peak is getting interference from another element, you may switch to the L simply because it's free of that interference. Wavelength dispersive spectrometry relies on providing a calibration curve on which you can analyze your own unknown samples and compare the peaks you're getting to the peaks you saw in the standards. Very robust analyses require a construction of a standard set that brackets and overlaps the materials you want to use. It's even most preferable to try to use materials that have the same sort of structural makeup to them, what we call the matrix. In other words, if you're going to analyze a feldspar, it's best if your standards are also feldspars. That way you're comparing apples to apples in terms of what the X-rays are having to encounter on their way in and out of the sample. Or in the case of an electron instrument, what the electrons are doing as they're going into the sample and the X-rays coming out. So a series of standards are usually acquired for the instruments. They have known concentrations. These have been typically analyzed by a myriad of a number of facilities to get highly robust, low error analyses on the elements of interest. That is then used to construct a calibration curve on which your samples can then be compared. It's important to do this frequently on many instruments because the nature of the intensities and how intense the peaks are may change with time as the tube sort of ages, as the instrument relaxes and does different things. So standardization is something that has to happen on a recurring basis. And again, really robust analyses almost require that you do this very close to the time when you're actually doing the analysis. This is what a characteristic wavelength dispersive spectra looks like. So you can see the peak there, a dashed line to indicate where the background is underneath the peak, and a lot of the spectra is actually background. This again is just characteristic radiation for, in this case, the element titanium. This is what a calibration curve can look like. So again, you take a series of standards, you look at its intensities on the day it's analyzed versus the concentrations that we know are there for a particular element or compound. In this case, silica, SiO2 is shown here. This series of standards brackets a range of silica compositions from mafic to felsic. It is pretty appropriate for analyzing igneous rocks. Again, it has a matrix that's very similar to any igneous rock we'd want to put into the instrument at that point. And on the right, we can see that the unknowns have been analyzed, and they map out where they fall on this curve. So we know their concentration by a given intensity for the peak we were looking at for SiO2, the K-alpha peak for SiO2. Also noted in triangles here are what we call internal standards. Really great analyses require that you actually send some known materials through that are separate from your standard set, but you know their values to see how your calibration curve matches up with known values. So ideally, you send the internal standards through, and they give you the correct numbers based on your calibration curve. That means you set up the instrument correctly, and the numbers you're going to get for unknown are going to be superb. Matrix is important because it factors heavily into what happens to X-rays as they enter the sample, and then how secondary X-rays try to get out. And the fate of a secondary X-ray can be very complicated. So let's say that we send X-rays into a sample if we're using an X-ray instrument, and we're looking for a particular element. It produces a secondary photon that would be characteristic, but then it goes and excites some other element and the energies gets trapped in that. That's lost. We don't get to count that one, even though it's there. So this is known as absorption, and it's the dominant problem that we have to deal with. There's also a small chance that your primary photon fluoresces a photon that of the right energies to actually excite the element you're looking for, the analyte, and then a secondary photon comes out that comes from that, and that's kind of like extra energy in that you didn't really see coming. Enhancement's rarer, so mostly we refer to this characteristic as absorption, but if we want to be full about it, it's absorption and enhancement. In X-ray instruments, we actually call the numerical adjustments that need to be made to account for absorption and enhancement as mass absorption coefficients. I won't go into the details on how these are generated, but it's a fairly complicated process that, again, ultimately what you're trying to do is make sure that the analysis you get actually reflects the concentrations you anticipate. And again, if you properly standardized and sent through some internal standards, you should have a pretty good picture that you've done a good job of this. On electron instruments, these are known as XAF corrections. They're doing this similar thing, although the mechanisms are different on electron instruments. So XAF stands for the excitation volume behavior, that density, particularly the element mass, makes a difference in the emitted intensities. A speaks to the absorbed volumes, and F speaks to fluorescence that happens in the excitation volume. All of this kind of adjustment to the data that the instrument is producing has to be done through calculation. And in the old days, it was a lot of after analysis calculation. First, using calculators or even more primitive calculating tools, and then eventually, on the computer on its own through spreadsheet systems. But it wasn't long before instrument makers started adopting the computer's power to actually do the corrections as part of the analytical tool. So most analytical tools today will do these corrections for you. You can specify what kind of mode you want. There are different ways to do the calculations, but most of the work can be handled internally, and the final result you get is already accounting for that. There are a number of different types of presentations we can make for results for the analyses we do through X-ray compositional analysis. These are two examples here that are commonly generated in my work. So on the left are individual point analyses on a feldspar. This is a very small volume we're analyzing on each feldspar, and we are able to graph out the concentrations of the three major components of a feldspar: the calcium aluminum component, the sodium silica component, and the potassium silica component on a ternary or three-axis diagram in terms of total composition. Not shown on this is the fact that there might be some differences between analyzing the center of the crystal and the rim of the crystal. That's something you can do as well, because again, these are really small targeted areas. We can get X-ray data from vanishingly small volumes of each mineral, and we're able to say things about those discrete compositions as we find them in individual mineral grains. And that really is the power of electron microanalysis through X-rays, is you can do very small areas. You can also do larger areas by rastering the beam, so that we saw in the electron maps, and certainly we could average all those values together if we wanted to see something over, the space of a few millimeters squared. If you want to know about, the entire material, what we commonly do when we crush up entire or whole rocks and analyze them in XRF is we ask questions about the composition there as well. Things traditionally in geochemistry that we present are the major elements attached to oxygen. So elemental oxides like silica here, or this is known as potash, potassium oxide, or sodium oxide here, soda. This is a common way to categorize rocks based on the compositions of the alkali oxides and silica, known as a TAS diagram. And we can see for this suite of rocks here that we have a well-representative suite that goes through basalts to basaltic andesites. I don't have many andesites in this particular suite. One that's on the dacite, trachy-dacite border, and then rhyolites. Most of the rocks are actually inhabiting the trachy trend up here before we get to rhyolite at the end of this. This is incredibly useful for talking about the rocks and actually speaks to some of the processes that are forming the different geochemistries that we see here. I've highlighted the use of X-ray sourced instruments to get characteristic radiations in X-rays as your exciter, and also electron instruments for doing the same thing. The modern analytical kingdom, if you will, has a lot of different options out there, and we can sort of explore that on a graph like here. This bubble diagram gives you a sense of how well you can determine concentrations with a given technique and how small the analytical volumes are. So two things we considered in this particular lecture is XRF up here. And you can see that it's pretty good for percentages. I'd actually extend it up to, hundreds of percents. But we can get down to tens of parts per million with that instrument. If you need smaller concentrations, then there are other instruments we can dial in to answer those questions. Wavelength dispersive spectrometry or energy dispersive spectrometry, basically what's under SEM here. Again, I think the SEM does a little bit better job than this nowadays. You can get to smaller concentrations, but if you really want to measure fine concentrations in point analyses, these are down at the micron scale, then the electron instrumentation is certainly useful for being able to do that. So, fluorescence produces characteristic X-rays when subjected to an energetic source. That energetic source could be an X-ray source or electrons. This will induce secondary fluorescence in a material. Electron instruments provide a means to microcharacterization, that is a point-by-point analysis. X-ray instruments generally characterize larger samples or whole materials. Energy dispersive spectrometry, EDS, is faster and cheaper and provides peaks as a function of the voltage. Wavelength dispersive spectrometry, on the other hand, tends to be more accurate and uses crystals through the Bragg equation. Peaks are assessed in terms of the crystal's 2 theta. You can zero in on specific wavelengths and really characterize the peaks that way. Robust analyses use a calibration scheme to compare unknown to known values. Care must be exercised in selecting and evaluating peaks because of the potential for interference. Intensities are adjusted for absorption and emission in these techniques, so we can account for lost X-rays or additional X-rays we didn't actually pay for in the energy we put in. And these provide the chemical composition of the materials. Comparison may follow once those compositions are known. Thank you for your attention and enjoy using X-rays.